Alright, distributions of data. This is our second lesson here in Unit 1-2, One Variable Statistics. And this follows from the stuff that we did yesterday, or in the first lesson, on graphing, when we were making frequency distributions and histograms. So the point of doing those histograms is to look at the distribution of data over its range. So what we want to do in this lesson is sort of look at the kinds of shapes that those distributions can form, so we can kind of classify them and talk about them. And we're going to see some of these distribution shapes later on in the course, and they're going to become kind of important. So we want to be able to create a histogram or frequency distribution for a data set using technology and paper and pencil, just like we learned in the last lesson, and then talk about the shapes of these distributions. So there are basically four general categories that we're going to be using in this course to talk about the shapes of distributions. So here's the first one, what is called the uniform distribution. So you can see the histogram over there to the right. If all of the frequencies as you go across over the range are approximately the same height, we call this a uniform distribution. Okay. Now, the histogram that they've given us here is titled the die rolling game. So it looks like what they're doing in this game is they're rolling a single die and they are recording the frequency or the number of times they get each one of those numbers up there. So I've asked the little question here, is this data discrete or continuous? So this is discrete data because that die can only take on the numbers 1, 2, 3, 4, 5, and 6. So sometimes you will when people are making reference to a histogram, they'll say that you can only do a histogram on continuous data. This is still a valid histogram here because the possibilities you get when you roll the die, 1, 2, 3, 4, 5, and 6, are all sort of, they encompass all of the possibilities here. So we don't have any gaps in between the things that we have plotted across our range or across our x-axis there. So even though down here we don't have intervals, we have specific values, this still shows the distribution of the frequencies across the entire range. Okay, so that's the uniform distribution. The next one is what is called the normal distribution. Okay, sometimes called a bell-shaped distribution or a mound-shaped distribution. And you can kind of see it in this, this example right here. It's roughly symmetric. It's got a peak in the middle and then sort of two tails off on either side. So if we just draw sort of a smooth curve here around the data that we have here, you can see this kind of this bell-shaped, okay, with a peak in the middle and then these two little tails that if we were to extend this graph would go off way out here to either side like this. Okay? So this is the normal distribution. Okay? What are they graphing here? They're graphing dice sums. So it looks like what they've done is they've rolled two dice and they are adding the numbers that show up on the two dice, and they're recording the frequency of how often each of those sums come up. So if this were classifying this data, it is going to be discrete as well because it can only take on those specific values. Okay? But this is still a valid histogram because the x-axis, even though again it has specific values and not ranges or intervals, it still encompasses the entire 2 to 12, sort of encompasses the entire range that you can have in terms of those dice sums. So we're still seeing the distribution of those sums over their range. All right, next up, bimodal distribution here, often called a U-shaped distribution. So why would they call it a U-shaped distribution? Well, here if we draw sort of a smooth curve showing the trends, we get a nice U shape like this. Now, it doesn't have to be like a U shape like this. The characteristic of a bimodal distribution is that there are two modes or two peaks in the distribution. The peaks don't have to be the same height like they are here, and they don't have to be at the ends of the range like they are here. Okay, so here we've got what looks like a better histogram to us because we can see now that what's plotted on the x-axis here are ranges of values, right? This one is going 400 to 450, and this is the number of scores in that interval from 400 to 450. Is this data discrete or continuous? It is discrete, I think, because the score that you can get in a game of Spider Solitaire is probably going to have to be an integer number, but we're getting close to something that could be considered continuous. A change in score of like 1 or 2 over when your total score is 850 or something like that. We're getting to the point where we can almost think of these things as being continuous. So here's another example of a bimodal distribution, which looks a little bit less U-shaped, but still has sort of 2 distinct peaks in it. And this is an example of a bimodal distribution that we actually encounter a lot in school. This is the distribution of test scores. So we have a peak here that represents the people who really studied, and a peak down here that represents the people who didn't study. Okay. So is this data discrete or continuous? We're probably getting to the point where this is continuous data, because that test score, I think, could be any number you want. It could be 85, 85.6, 85.62, something like that. So this is continuous data. Now, the question I asked down at the bottom there, can you spot the problem with this histogram? This histogram, I think, is improperly labeled. I think when they put 10 here, labeling this bar, what they really mean is a range of scores that go from 10 to 20 possibly. And then they want the next one here to actually go 20 to 30. And so on and so on and so on. Now, let's see, that creates a bit of a problem here, because then this one over here would go from 90 to 100, and then I don't know what this bar over here represents. So maybe I've done this wrong. Maybe this one here is supposed to be 90 to 100, and this is 80 to 90, and so on and so on. So then this one down here would be 0 to 10, and this one here would be 10 to 20. The fact that I can't tell what that axis is really supposed to be is a problem with the graph. This graph isn't very clearly labeled, so it's not doing a very good job of presenting the information that whoever made this graph wants to present. So the good things about the graph are that the axes are labeled. We do have test scores, we do have the number of things or frequency up here, but the x-axis is improperly labeled. All right, finally, our last category here are what we call skewed distributions. So skewed distributions are distributions that are like a normal distribution but are not symmetric. Okay? So a normal distribution has a peak in the middle and 2 tails off to either side. In a skewed distribution, one of the tails, either the one on the left or the right, has been extended, or it has more data in it than we would expect in a normal distribution. And that's how we name them. We name them either left skewed or right skewed. So in a left skewed distribution, we have more data on the left side, or the left tail is a little bit bigger. Or maybe a little bit longer might be a better way of saying it. More stuff on the left. In a right skewed distribution, there's more stuff on the right. And I should specify that we mean the tails here. Right tail and more in the left tail over here. Okay. So it's not the location of the peak, it's how much data is in the tail of the distribution. Okay. So when we're looking at these scores here, solitaire scores, I think we can still classify these as discrete, but the possibility that we might think of them as being continuous here. And when we look at our left skewed distribution, well, I've asked again, can you spot the problem in this histogram? The problem is, number one, this axis is not labeled, so we don't know what these intervals that are being plotted across the x-axis actually represent. It looks like these represent years. Okay, 1930, 1950, 1970, 1990, 2010. If that's the case, then this wouldn't actually be a histogram, okay, because then those wouldn't represent proper intervals. Okay, this would be a bar graph basically. Okay, so we're not sure what's going on in there. So we can't really say, because we don't know what's being graphed, we don't know whether this is discrete or continuous, because we don't know what that x-axis represents. Okay. All right, so finally, this was the histogram that we made in the previous lesson. Time to assemble a tricycle in minutes. Is this, well, first of all, what would we say is the shape of this thing? Well, it starts out low, it increases up into the middle here, and then it decreases as we get over to the end here. So this would be an example of a normal distribution. Now, why do they call it a normal distribution? Some people have said they call it the normal distribution because this is the most natural distribution that data follows when you are measuring things. Um, you can think of almost anything that you're trying to measure, and you tend to get a lot of people sort of in the middle here around the average, which is why you have a peak, and then a small number of people who are much larger or take much longer, and then a small number of people who are way down on this other extreme end. And most of the people are just kind of average in the middle. Okay, so we're going to be looking at the normal distribution a lot when we get to unit 3 in this course, and we'll look at how you do a lot of different statistics with using the properties of that normal distribution. Okay, and just to finish off here, is our data here discrete or continuous? Well, these were times, we were measuring them, so these are going to definitely be, this is a continuous quantitative variable here.